Hello.
Hello.
Yeah, can you hear me?
Yes, sir. Yes, sir. Good afternoon, sir.
Good afternoon.
Shall we start, sir?
Yes, this is Shailesh.
Yes, I'll just introduce. Good afternoon. I welcome you all to the second session of second day for the IEEE SPS event on latest trends in machine learning for signal processing applications. We have a very dynamic speaker now, Mr. Shailesh Sakri, Director, Automotive Audio Software, Herman International and Chair, also IEEE SPS Bangalore Chapter Chair. Shailesh sir is currently working as Director SW Audio Herman International and is responsible for car audio solutions like audio personalization, ANC, road noise cancellation, vehicle noise compensation, audio equalizer, surround sound audio, and other audio features to major car audio manufacturers worldwide. He has 22 years of industrial experience in the field of audio signal processing. He has worked in the capacity of Director of Audio Algorithms in Novels, which is formerly the Audience Incorporation, and manager in Amazon Lab 126. He earned his bachelor's degree from Gulbarga University and a master's degree from BITS Pilani. He has extensively worked on noise suppression and echo cancellors, which were adapted into major smartphones like Apple, Samsung, Xiaomi, LG, OnePlus, etc. Mr. Shailesh worked in Amazon Lab 126 and was leading the team which delivered the industry's leading smart speaker products, the Eco series. He was the lead for delivering the Eco shows such as Eco Show, Eco Spot, Eco Show 5, Eco Show 8 series of products along with Amazon's first premium Eco product where the users gave superior as a superior audio device greater rating. And Shailesh sir was also responsible for delivering the Eco Dot, which is Amazon's leading Alexa device with a close to 100 million devices that were sold worldwide and users gave a rating around 5. He currently holds 7 issued and pending patents. He is currently serving as a chairman of IEEE Bangalore section signal processing chapter. I welcome you, sir, for this session. And I just wanted to tell you, I am also an alumni of Gulbarga University 2000 batch, sir. Welcome to the session, sir.
That is good to know.
Thank you, sir.
Thank you.
You can take on the session.
All right, give me a sec. Just one. All right. Can you all see my screen?
Yes, sir.
Okay. All right. Thank you all. So today's topic, I'd like to briefly discuss about some of the machine learning trends in signal processing. Mostly, I'm going to touch base upon the ASR systems. Okay. All right. So firstly, so in the background is that so it's a deep structured learning. I'm pretty sure everyone would have heard about all the deep learning. So the deep structured learning, or most commonly the deep learning or hierarchical learning, this is emerged as one of the new era in machine learning research. And during the past several years, this technique developed from the deep learning research have already been impacting a very wide range of signal and information processing work within the traditional and the new and widened scopes, including some of the key aspects of machine learning and artificial intelligence. Okay, so What is deep learning? Deep learning is nothing but some human information processing mechanism. Could be a vision or audition that suggests a need for deep architectures for extracting complex structure and building internal representation for such from rich sensory inputs. So what are these sensory inputs? It could be visual, this could be any sort of inputs, the sensory inputs. So the human speech production and perception systems are both equipped with clearly layered hierarchical structures in transforming the information from waveform level to the linguistic level. So that is how even most of us, of our brain also perceive it. So whatever we hear, whatever we view, all those the visual and auditory signals transform them into linguistic ways, and it gets broken down, and that's how our minds also gets visualized. Okay, right. So and deep learning is all about learning multiple levels of representation and abstraction that help to make some sense of data such as images, sound, and text. And see, I mean, this all this human information processing mechanisms, the vision and audition, suggests that there is a need for deep architectures, right? So when I say the deep architecture, you need to have some mechanism of extracting complex structures and building some internal representation from
Actually,
such. Uh, can you all hear me?
it's on the slideshow, sir.
Oh, is it off?
No, no, slideshow, I'm asking.
Okay, fine.
Thank you, sir.
Is this okay now?
No, sir.
Okay.
Sir, full screen mode.
No, no. Full screen mode, sir.
Okay, it's not in a full screen mode. Okay, just
Actually, below.
just
The
a,
yeah.
just a minute. Probably.
No, no. Actually, he shared the entire screen only, but he did not on the full screen mode.
Give me a sec. Just a minute.
F5 will work.
Yeah. So I'm working on multiple monitors. That's why there's a confusion. Can you see my screen now?
Yes, sir. Thank you.
Yes. Okay. That's good. Okay, you can see my screen now, right? In a full screen mode. All right. Sure. All right. See, this historically, all this concept of the deep learning originated from all this artificial neural networks. Okay, so occasionally we also hear about this new generation neural networks, right? So this feed-forward neural networks, the deep neural networks. These are all the good models. I mean, good examples of models with the deep architecture. So all these things were becoming popular in 1980s, and more so, it's becoming more and more popular. And this use case is, I mean, we are in a situation that we are able to realize all these structures because of very powerful computational mechanisms that we have, all the powerful computers that we have. That's one of the reasons why all these machine learning concepts are becoming very most and most popular. Okay. So quickly touch basing upon hype circle. So I don't know how many of you all have heard about this hype circle. So hype circle is nothing but it represents the five stages. It represents the maturity, adoption, and the social application of specific technologies. Okay, and hype circle claims to provide a graphical and conceptual presentation of the maturity of emerging technologies through 5 phases. And what are those 5 phases? The five phases are the technology trigger, peak of inflated expectations, trough of disillusionment, slope of enlightenment, and plateau of productivity. Okay, and this is the hype circle of all the machine learning expectations. Okay, as you can see here, there is a technology trigger that you could see it's peaking up, and there's a peak that was a lot. There's a lot of expectations. Okay, and I believe we have already passed through that phase, and we are kind of in a plateau of productivity, I would say, and that's where we can see this. We have heard about all these. The natural language understanding, the big data, okay, hybrid cloud computing. I mean, there's a lot of applications and a lot of technologies that have been floating around. And the expectation, there was a period there was a lot of expectation, and obviously, when such thing happens, there's a pressure on the computational stuff. I mean, having more and more powerful computers to realize some of these deep structures. So on the similar thing on the hype circle on a deep learning, applying this Gartner hyper circle to the artificial neural network development. So this is one of the thing that you can see over here. There's a technology trigger that was there in the early 1980s, and it was kind of peak somewhere in 1990s, and there was a lot of research that went on, obviously, and then there was a technology trigger. Okay, then trough of disillusionment over there somewhere here. The people were disillusioned because the expectation was a lot, right? And then slowly it started picking up, I would say. Okay, so as I was saying, I briefly want to touch base upon this. Obviously, when we go through all this different applications, okay, there's a lot. I won't be able to touch base upon most of all these things, but one thing that I would like to discuss in today's discussion is the automatic speech recognition. Since I come from the speech and audio background, this is much closer to my heart, and it makes sense for me to speak confidently about this and talk about this. Okay, so what is a ASR? ASR is nothing but the automatic speech recognition. ASR is a conversion process from the acoustic data sequence of speech into a word sequence, breaking down all these the speech into recognizable words which can be interpreted and you can make sense of it. Okay, although you'll somehow be able to break it down, but making a sense of that is also a very important thing. So from a technical point of view, what you can say is that machine learning, this conversion of the process of ASR requires a number of sub-processes, including the use of discrete timestamps called the frames, and to characterize the speech waveform data or acoustic features, and the use of categorical labels like words, phones, and the triphones to index the acoustic data sequence. So the more interesting and unique problem in ASR, however, is on the input side, caused by the variable length acoustic feature sequence. The reason why I call it as a little bit problematic over here is that, you have to. I'll touch base upon that in the. So let's go on the next one. So probably I'll explain it in detail over there. So even if we have two output word sequence, even if two output word sequences are identical, this is another problem. But even if you have two identical sequences, word sequences, the input speech data typically have a very distinct lengths. Okay, and so different input samples from the same sentences usually contain a different data dimensionality depending on how the speech sounds are produced. So the reason why I say how it is being produced is because where you're talking and the acoustic environment of this makes a big difference, right? So that's why it's very, very important that, I mean, to also take into account some of the acoustical aspects of it, okay? And so this is a very classic speech recognition system. So when you have a speech signal, you have a feature extraction, and then there's a comparison. There is an acoustic model during a comparison also, and then there is a word search with the lexicon dictionary, and then there is a decoded word, then there is a word sequencing that happens, then you have to form a sentence from those word sequencing, and there's a language modeling over there, and then you form a sentence, okay, which you can interpret it, right? So all that we are talking about, it's the more interesting and unique problem in ASR, however, is in the input side, which I was talking about, is caused by this variable length acoustic feature sequence. So see, ASR is a very difficult task due to the huge number of variabilities with complicated and non-linear interactions caused by the speaker. So it could be accents, it's a dialect, it's a style, it's a motion, then it's a co-articulation, then reduction in the pronunciation. My pronunciation might be different from other pronunciation, and then there's a hesitation, there's emotions involved in it. And on top of all those things, there's an environment, like I was talking about. There could be a noise, there could be a side talk, there could be a reverberation, and another added challenge will be on the device. Like, are you talking from a headphone? Are you talking from a speakerphone or the cell phone? The sensitivity of the microphone, all those things matters a lot when you would like to have a very good the ASR system. Okay, so this is a very traditional ASR system. This is a classical speech recognition. Okay, just a minute. So what you can see over here is a classical speech recognizes the. So you have this speech which goes through something called the substitute feature extraction and the multi-feature cluster, so MFCC features. Then based on that, you derive the Gaussian acoustic model, and then the phone likelihoods. Then there's a HMM lexicon thing, and then there's a Vitabe decoder. Okay, so this is a brief thing about this traditional ASR system. However, before I touch base upon some of the limitations of this traditional ASR system, I'd like to touch base upon this problem of the speech. So in most of the problems, what we are trying to solve is with the machine learning or the deep learning, we have to set some inputs that we'd like to map to a set of outputs. So mostly each input corresponds to some sort of outputs. So let's assume that if there is some function f of x, and that can map to all these inputs to some corresponding outputs. So the problem with the speech is that our feature vectors are taken from a very short time spectra. So when I say the short time spectra, you're breaking that. You cannot process everything at a very broader level. So you have to break down into some frames. Okay, which means that we have some feature vector for every 20 to 25 milliseconds. Like the speech is usually typically processed at 20 to 25 milliseconds every frame. So what you have to do is that you have to get some feature vector for every 20 to 25 milliseconds. So the problem is if we don't know where this boundary is between each one of the sound. So when I say the phoneme, like these phonemes can split across the frames, right? It can be some portion of the word will be one frame, another portion of the word will be another frame. So if you could open a speech signal in any tool like Adobe Audition, so any sort of editing tools, and you cut the signal into say 200 to 300 milliseconds, and you listen to it without any context. you just can't make any sense out of it because it's just impossible. It's not possible to distinguish which sound it is. Okay, observe the data that, I mean, any phone, right? So we do not have a data about where the word ends and where the word begins. This is a challenge, right? This is a challenge about all this ASR system. Um, it's a very complicated thing, right? And on top of that, you have to make some sense out of it, correct? So from the input sequence, what you do is that you are extracting some feature, and then from acoustical point of view, you are going to have a phone or a triphone, and that are built in the training stage for a comparison, and most likely a model is chosen based on that. So concatenating the chosen acoustic and units and words that can be obtained, and confirming from this, from searching a lexicon, a simple grammar gives you some sort of word sequence. And from there you finalizing the speech recognition. And for the speech recognition process, what we need to know is that we need to have as a knowledge resources a lexicon in which is contained a phonetic transcriptions of all the words that can be recognized by the system. Okay, and imagine this is, I'm talking about, and every language differs because what matters is the lexicon over there, right? So that's why we have the ASR system for every language is totally different. So to realize a very correct word sequence, in other words, to realize a very speech understanding, speech understanding are being introduced in constraints in form of some restrictive grammar or language modeling. Okay, so there are features like the Mel frequency spectral, Mel frequency septal coefficients, MFCC. This is a very perceptual linear prediction coefficients. So what it does is that it extracts some of these features, okay, and compacts everything in there, so that, I mean, a very meaningful information can be extracted out of it. Okay, so they are obtained by this DSP technique. So in this way, there is some, some sort of extraction and then making some meaning out of it. Now, what is the problem with this traditional ASR system? So the problem, the first one is this stepwise refinement. So the stepwise refinement is nothing. Now, there are many module specific processes which are required to build an accurate model. So take for example, when we build an acoustic model from a scratch, we had to build some with the HMM hidden Markov model and Gaussian mixture models to obtain a very tight state with the HMM structure and some phonetic alignments. So before we can train any deep neural networks. So this is a, very stepwise extraction. And then you should have linguistic information to factorize any acoustic and language models very well. What we need to have is some lexicon model, which is usually based on a very handcrafted pronunciation dictionary, which can map a word into phoneme sequences, right? So such phonemes are designed using a linguistic knowledge, which are subject to human error also, that a fully data-driven system might avoid. So finally, some language that do not explicitly have a word boundary need to be tokenized, need some tokenization modules. And the third limitation is this conditional independence assumption. So what is this? The current ASR system often use some conditional independence assumption, example, especially the Markov assumptions during all this above factorizations. And to make use of the GMM and the DNN and any models. So the real world data, do not necessarily follow such assumptions, leading to some sort of misspecifications. And then there's a complex decoding also. What do you mean by complex decoding? So there is an inferencing and decoding. It has to be performed by integrating all the modules. So the decoding is now, if you can see over here, there's a bit-to-bit decoding. So everything you have to take into consideration. There's a lexicon, everything, and then you have to do the decoding jointly. Okay, so this is a very complex decoding. Although this integration is often efficiently handled by some sort of fine state transducers, everything, but the construction and implementation of this well-optimized transducers is, is a little bit complicated. Okay, and then incoherence and optimization. So all these above models are optimized separately with different objectives. Like the MFCC is, optimized it in a different context. The Gaussian acoustic model is optimized in a different context. All these different modules are kind of optimized in coherence, not incoherent, where each module is not trained to match each other modules. Okay, so what you're dealing with is all the scattered devils, right? So that is the problem with this traditional ASR systems. Okay, so now the next one. Then what is the best way to move around? So the best way to solve all these problems, like what we had, is all the scattered one. So maybe what we need to have is a model where you can optimize it together. It's a joint optimization. So you don't have to worry about each one of these modules, right? And this is called the end-to-end model. Now, what are the advantages of these end-to-end model? So there are several advantages of the end-to-end model, or the traditional, it could be all these hybrid models. First, the end-to-end models use a single objective function, which is consistent with the ASR objective to optimize the whole network, while the traditional hybrid models optimize individual components separately, which cannot guarantee a global optimum. So therefore, what we can say is that end-to-end models can outperform traditional hybrid models, not just what you experiment in academics, but also in the industrial realization also. And the second thing is because the end-to-end models have directly output characters or even words, it can greatly simplify the speech recognition pipeline. So what you can say, in contrast, the design of a traditional hybrid models is complicated, which requires a lot of expert knowledge with years of ASR experience. Okay, and obviously because it's a single network. Okay, so because it's a single network which is used in a ASR, the end-to-end models are much more compact than the traditional hybrid models. Therefore, the end-to-end models can be deployed to devices with a very high accuracy and the low latency also. In the earlier model, you had to take care of the latency at each of the stages, each of the models. But in the end-to-end model, you don't have to worry about these kind of things. Okay. Now, while a few things I can add is that while there's an end-to-end models, just a minute. While end-to-end models can achieve the state-of-the-art results and most of the benchmark in terms of the ASR accuracy or the hybrid models, which are still used in large population of commercial ASR system. But there are a lot of practical factors such as that we have to take into account is the streaming, the latency, then there's adaptation capability, which affect the commercial model deployment decision. So the traditional hybrid models are typically optimized for production for decades. We all know the HMM, GMM models, everything, and even the MFCC, when we have been hearing. All these, the end-to-end model is a very recent trend. And then it is very hard for end-to-end models to be easily commercialized. So, but there is a constant effort still going on, okay, to realize all these end-to-end models. So the accuracy, of these, all these ASR system has, should be significantly will be boosted with the deep neural networks and based on the hybrid model that we have been seeing in all along. Okay, such breakthrough used with the used DNN to replace the traditional GMM models for acoustic likelihood evaluation, while still keeping all the components such as acoustic model, language model, and lexical model, etc. And it's a very challenging thing, I would say. So what are the recent so these are some of the recent advancements that I talked about. So the speech community is seeing a very significant trend in moving towards this, from the deep neural network based hybrid modeling to end-to-end modeling for automatic speech recognition. So and the speech community has a new breakthrough by transitioning from hybrid model to end-to-end modeling, which can directly translate an input speech sequence into an output token sequence using a single network. Okay, that's accomplishment, I would say. So in end-to-end models, these are, although there are many popular techniques, also what we can categorize is that there are three different techniques that are being used. One is called the connectionist temporal classification, the attention-based encoder-decoder. Then there is a recurrent neural network transducer. So these are the simple blocks of CTC. There's an encoder, there's a decision with the soft max, and then make a decision. This is a very simple structure. And with the AD, there's an attention-based encoder decoder. There's a module called attention, and then there's a decoder. Okay. And then what you have is with the RNNT, recurrent neural network transducer, you have an encoder just like over here. Then there's a prediction also. So then there's a joint optimization between the encoder and the prediction, and then you arrive at some prediction. Okay, let's briefly touch upon these the connectionist temporal classification. So this connection, the CTC technique was designed to map the speech input sequence into some output label sequence. Okay, because the length of the output label sequence is smaller than the input speech frame, what they do is that they insert some sort of blank label between the output labels to allow some repetition to construct CTC paths, and that have the same length as the input speech frames. Okay, so this is how they try to insert over here. Okay, so CTC was the first end-to-end technology that was widely used in ASR systems, some ASR systems not commercially available, but there was an attempt that was made. But however, this conditional independence assumption in CTC is most criticized because there is no prediction or nothing. So you're trying to break it down and filling in a gap wherever you want. So one way to relax this assumption was to use some sort of attention mechanism, which can introduce some implicit language modeling across the speech stream. Okay, so that obviously posed some challenges. Okay, and that's why then there is attention-based encoder-decoder. Okay, so what is attention-based encoder-decoder? AD has some sort of encoder network, an attention module, and a decoder network. The encoder network performs the same function as the encoder network in the CTC. Okay, what we had, and it will by converting the input feature sequence into some sort of high-level hidden feature sequences. Okay, so the attention module will compute the attention weights between the previous decoder output and each frame of the encoder output using some sort of attention. So if you can see over here, based on the previous decoder thing, so there will be attention that will be done, which can generate some sort of context vector as a weighted sum of encoder output. Okay, so then the decoder network takes the previous output label together with the context vector to generate some sort of its output to calculate some prediction, which is operated in an autoregressive way as a function of the previous label outputs without the conditional independence assumption. Okay, so but what I can say is that there is all this all streaming AD modules. Streaming is a very important thing, and I talked about the latency also. Okay, so one sec. Okay, sorry, there is some distraction. Okay, all right. Yes, what I was talking, AD. Yes, all these streaming AD modules need some complicated strategies to decide the trigger point of the streaming. Okay, because it has to be very instantaneous, everything. Say ADs can also cannot perform very well in some of the long utterances. So therefore, although there are some many activities in the areas of streaming of the AD modules, industry has slowly trying to adapt to this RNN kind of transducer. So RNN kind of reason is mostly because of some of the latency that it can beat, as well as it's some sort of the streaming that you can easily get around with it. Okay, so so as you can see in all these models, there's an encoder which is pretty common. So encoder is a pretty common. So all these encoders, most of the encoders use the LSTM kind of structures. So most of you might be aware of this LSTM, the most popular model unit. Okay, so the encoder can be either multi-layer unidirectional, LSTM, RNN, or any sort of structures. So it's very deep to go in, but I'd like to only touch base upon it at a very top level. So even with this encoder, there are various mechanisms by which you can encode it and extract meaningful information out of it, which you can interpret about it, right? So see, all the earlier models that we had that was designed were not taking into account some of the speech characteristics of it, but all the models that coming out very lately are taking into consideration most of the characteristics of the speech, and also the most striking characteristics of the speech is the history that runs across. It's not like the history is embedded within one frame, so it runs across the frame to make any meaningful decision out of it. So that's why it's very important to choose what kind of encoders you want to use, and obviously based on the encoder you have to choose the decoder. And most importantly, the data also, kind of data that you do and the tagging how you make it also makes a big difference. So the more kind of data you have, you can get a very good model out of it. Okay, so what we can conclude is that all these I just briefly described about all these end-to-end models and some of the practical technologies that enables the end-to-end model, and how to surpass these hybrid models, not just in academic class, but also in industries where you can replace the hybrid models. Okay, although this CTC is revived and it's advanced encoder, all these advanced encoder structures are there. The most popular end-to-end models are the AD and the RNNT. Okay, because of this streaming nature, research has been gradually shifted from AD and RNNT. Okay, the encoder is most module in the end-to-end model, which attracts most research, because as you can see from that structure that I showed, the encoder makes a big difference over there. So as of now, the trend seems to be very clear that encoder structure has shifted from LSTM kind of thing, which to transformer and some of these variants. Masking strategies also used to design some efficient transformer encoders, because the speech there is, when you hear it, your all this interpretation should be based on the masking technology of our ears. So the masking strategy is used to designing some sort of transformer encoders. And most importantly, what we should also have is some low latency and a very small computational cost for the industry applications. So not just that, in order to serve some multilingual users also, There are multilingual end-to-end models are also trained by pulling in all the language data together. However, there is a very, very clear accuracy gap between the multilingual models with and without language ID. Okay, because the more you plug in, I mean, lexicon becomes more challenging, internally reinterpretation becomes a more challenging thing. So configurable multilingual model can fill this gap by training the model once, and how it is being configured on the language selection and all the multilingual uses. So adaptation may be the most important area to work on in order to enable this end-to-end models, which can replace the hybrid models in the industry. Because of this huge accuracy improvement with adaptation to very new speakers and the new domains. Okay, so and specifically there's more research on domain adaptations and customizations than the speaker adaptation. So I mean most of the models are on the work that has been done, it works perfectly fine in a very, very clean environment. But I mean, adapting all these things, various noisy conditions, various kind of talkers, and some sort of side talkers out there, the multi-talker becomes very, very challenging thing, because I'm talking something. Okay, there are other users who are around me who are also talking about it. Now there is a crosstalk over there, and what will the system should interpret? Is this your voice? So I mean, you need to have a mechanism which can track this dominant speaker and interpret only those words, right? Only them, rather than who are speaking, surrounding us, right? And the same is applicable to noise also. So what kind of noise makes a big difference? I mean, the noise conditions in every geographical regions are way different than, like the US, the background noise condition is way different than the Asian background noise condition. The Indian noise condition is different. Chinese noise condition is different. US noise condition is different. Even the noise profiles that have been recommended by the standards are mostly the European noise standards. They are not taken into account some of the Indian noise conditions. But Microsoft, Google, Amazon, they are all working on gathering more and more such noisy information, which by which they can make all their models very, very robust. Okay, I'm pretty sure with so much of traffic around, like to go to my office. I'm staying in Bangalore. To go to my office takes couple of hours for me to reach office. Okay, in one way I'm saying. So if I go to office on daily, so it will take around 4 hours just to and fro. Okay, so but you might have some calls in the middle also. Okay, and there is a background noise, and you'd like to have some of the ASR systems also, like whatever you want to use. You want to interact some of your devices with a voice technique. So that there are only two interfaces which are becoming very, very popular. The UI is obviously very popular. You also want to interact with the devices from your voice, right? So not just with your phone, even with your hand, not just with the handheld devices, even with the home devices at your home. You might say, Alexa, turn off the light. Alexa, switch off the light. Okay, or hey Google, please close the door, whatever. So there are many devices, security devices, many devices within your system, which you call it the Internet of Things, right? Sorry, my phone woke up because of hey Google. Okay, so there are many such things which are connected through the internet, and you want to interact with all these devices from your voice, right? So robust noisy, robust voice, robust no word error rate, I would say. Obviously robustness is very important thing. The accuracy is very, very important thing, which can make this product better and better, right? So efforts are on. There are many things that are happening. I cannot talk everything in this forum. So um, I mean, there's a lot that's going on. I mean, there's adaptation, there's a speaker adaptation, domain adaptation. Okay, there's a lot of customizations. I mean, more and more advanced models are also being tried out. But in general, what I can say is that all revolves around these basic models that I showed around. There could be a mix and match, and how you can make some of these the encoders, how we can mix some of these transformers and encoders together, how we can make these predictions together and work out, okay, and make all these models better and better. Okay. So this, I'd like to conclude my short talk. So uh, welcome to have any questions.
Participants, any questions? Sir, may I ask one, sir?
Yes, sir. Yes, ma'am. Please.
Sir, can you throw some light on what kind of challenges the research community in audio signal processing has, like what
Specifically in terms of the speech recognition or in general, you're saying?
in speech recognition, sir?
Yeah, speech recognition, as I said, the accuracy, see in a clean condition, I mean, you can also try it out. The Google recognition works very fine, or for that matter, even in Alexa devices, everything, all these recognition works very fine in a clean conditions. Okay. Because that's how the models are trained, and there is no problem with the, I mean, interpretation or recognition. The challenges comes with any sort of noise conditions. Okay, like the baby screaming, there's one sort of cross talk, or you're talking and there's I mean, there's some sort of background talk. I mean, very popularly called the pub talk. Okay, like the kind of noise you hear in the pubs. Okay, so that is also one of the challenging noisy condition. Okay, and one thing that most of the researcher in US would not consider is the fan noise. The fan noise is a very popular thing in India, which you won't find it in Europe or US market. Okay, so and this fan noise, I mean, if that fan is very closer to the especially with the table fans that we have, that sort of becomes a directional wind. Okay, so it's not like a, I mean, all distributed wind within the room. Okay, then it becomes even more challenging because there's a heavy low frequencies and with the wind, and your voice also will be in the low frequencies, and the interpretation becomes more challenging. And when you're going to break it down, during this breakdown, your interpretation might go haywire, and that's where your accuracy will hit a lot. Okay, so with the handheld devices, you can try it out while you're moving in a car. Try out this handheld devices with the Google ASR. It's terrible performance. Yeah,
Thank you, sir. Thank you, sir.
thank you.
Thank you, sir, for your elaborate talk on ASR systems, that is automatic speech recognition system, and you gave us a big picture of it, like how we have been using these traditional ASR systems, and because of those limitations, now people are moving towards this end-to-end models. And you also explained some of the end-to-end models like connection, temporal classification, attention-based encoder, decoder method, and RRN transducer-based method. Thank you, sir. It was a great session.
Thank you, madam. Yeah. So, by the way, which college you are from?
Sir, PDA College, sir.
Okay.
Puja Papa College.
Thank you. Thank you.
Sir, please accept as a token of gratitude this virtual memento.
When am I going to get the real memento? Just kidding. Yeah, sorry. I mean, I really wanted to travel. I had a wish to travel, but there's a lot going on in office. So
Yes.
I'm just sneaking out some time out of my office hours and having this talk. So
For future, sir.
yeah, thank you.
Thank
Thank
you,
you.
sir.
Thank you. All right, so I'm going to hang up then. Thank you, everyone.
Yes, sir. I request all participants to be back by 1 o'clock for the next session.